How many ways can we place 8 rooks on an 8x8 chessboard in such a way that no rook can attack another? Here's one possible arrangement satisfying the rules. We can see this is true because rooks can move vertically in one column or horizontally in one row. So we're essentially trying to place 8 rooks on the chessboard so that no 2 rooks are in the same column or the same row. Here's a few more such arrangements. How can we count these without listing them all out? Is there some possible techniques we can use? In this video, we'll encounter 2 counting principles. The first one is known as the sum principle. The sum principle states that if an event A can occur in m ways and an event B can occur in n disjoint ways, then the event A or B can occur in m plus n ways. We see this as a direct translation of the sum principle for sets by noting that if we have the sets A and B and they do not overlap, then we can determine the cardinality of their union just by adding the cardinalities of the separate sets, as seen here. The sum principle can be generalized to more sets. So if we have sets S1 up to Sm, and there are Ri objects in each set Si, then if the sets have no elements in common, the number of ways to select a single object from one of the M sets is given by the sum of the total numbers of elements in the sets, which is R1 plus R2 all the way up to adding Rm. Let's see an example of this. How many lines are there connecting the 5 dots shown below here? If you watch carefully, it gives an idea about how to think about this problem from the perspective of the sum principle. We can decompose the lines into 4 disjoint sets. The first set is the collection of lines that are connected to the blue dot. The second set are the lines connected to the pink dot but not the blue dot. The third set are the ones connected to the yellow dot but not the blue or pink dot, and the last set is the one connected to the green but not the other 3 colors. So the total number of lines by the sum principle is 4 plus 3 plus 2 plus 1, which is 10. Have another go at this yourself, but this time, let's figure out how many lines there are connecting the 10 dots in the diagram below. If you watch carefully about how this diagram is built, you might be able to see the sum principle in action. The second important counting technique is known as the product principle. The product principle states that if event A can occur in m ways and each possibility for A allows for event B to happen in exactly n ways, then the event A and B can occur in m times n ways. We can think of this as a direct translation of the formula for the cross product from set theory, because event A and B corresponds to an ordered pair of something from A followed by something in B. The formula for the cross product can be determined by taking the set A and putting a copy of B on top of each element in the set A. Then we can pair each element from A with a corresponding element from B. What we are left with is a grid of size cardinality of A by the cardinality of B. The resulting interpretation is that the cardinality of the cross product A times B is equal to the product of the cardinalities of A and B. The product principle can be extended to multiple sets. So suppose a procedure can be broken into m successive ordered stages with Ri possible outcomes at stage I. If the number of outcomes at each stage is independent of the number of choices in previous stages, and the outcomes are all distinct, then the procedure has the product R1 times R2 up to Rm different outcomes. Let's work out a straightforward example. How many strings can you create by rearranging the letters in the word math? Well, one thing we can do is that we can literally list them all out. All we have to do is be careful to make sure that we haven't repeated any of the words or strings that we've seen before. What we end up with is this list. But notice in this list, we've already done something interesting. We've organized them by the first letter, M, A, T, and H, and then within each column where the first letter is fixed, we notice that the number of second letters that can appear is the same each time, and then the number of third letters is the same, and then the number of fourth letters is the same. Our enumeration shown here gives us an idea about how to understand the product principle. We will organize the strings in a tree diagram. The first level contains the first letter of the string, the second level contains the second letter of the string, the third level contains the third letter of a string, and the fourth level contains the fourth letter of the string. So the strings correspond to paths from the top to the bottom. Now we see that we can do our counting using this tree diagram. So the total number of such strings comes from a path in the tree. We have 4 choices for the first letter, and then no matter what letter we choose, there are 3 choices for the second letter. And no matter what pair of letters we choose first, there are 2 choices for the third letter. And no matter what triple of letters we pick, there's 1 choice of letter for the fourth letter. Since the number of choices is independent at each stage, we can multiply the numbers together to get that the total number of strings is 4 times 3 times 2 times 1, which is 24. Even though the sum and product principles may seem kind of elementary, they can actually be utilized to do some very powerful counting. The idea is that we can provide complex counting arguments by merging the 2 principles. We may describe the objects so they can be built in ordered stages and apply the product principle. We can break the objects into 2 sets with nothing in common and apply the sum principle. And then once we're trying to figure out the number of things that can happen at a stage or in a disjoint set, we may have to repeat the process. Let's try this out with an exercise. How many passcodes are possible on a phone that allows either 4 or 6-digit passcodes? Pause the video and try this first before our discussion. The word "or" already tells us what to do. It tells us to break it into 2 disjoint situations where we either choose a 4-digit passcode or we choose a 6-digit passcode. These cannot overlap. Now, if we focus only on the 4-digit passcodes, we see that we have free choice for each of the digits. So we can simply press some digit, then a second digit, then a third digit, then a fourth digit. This means, since we have 10 choices for each digit, we can apply the product principle, and we see that there are 10 times 10 times 10 times 10 total such passcodes. The same analysis works on the 6-digit passcodes. We get a 6-digit passcode by just choosing the first digit, the second digit, the third digit, the fourth digit, the fifth digit, and the 6th digit, independently of the previous digits. Because there are 10 total digits, the product principle tells us that there are 10 times 10 times 10 times 10 times 10 times 10 total such passcodes. Using the sum principle, then, we get the total number of passcodes as 10 to the 4th plus 10 to the 6th. We have applied both the sum principle and the product principle to determine the total number of possible passcodes on such a phone. Let's revisit our question that started the video off about non-attacking rooks on a chessboard. Recall that we wanted to know how many ways we can place 8 rooks on an 8x8 chessboard in such a way that no rook can attack another. We can answer this question by applying the product principle, by noting that each column must contain 1 and only 1 rook, so we can go column by column as our ordered stages. In the first column, we have 8 choices where we can place the rook. But once we place a rook, we remove that column and its row, so that now in the second column, we have only 7 choices for where to place the rook. Again, it removes the column and the row, so in the third column, there are only 6 choices for where to place the rook. It removes the column and the row, so that in the fourth column, there are 5 choices for where to put the rook. But once we do that, we remove that column and that row. Now there are only 4 choices for the next rook. Once we place it, we remove the column and the row. So the next rook has only 3 possible choices for where we can place it. Once we place that rook, we remove the column and the row. So the second to last rook has only 2 choices. And once we place that rook, we remove the second to last column and that row. Therefore, there's only 1 place left to place the final rook. Even though we showed just a single example, we see that the number of choices is the same in any given arrangement that we might create, and therefore the number of choices is independent of all of the previous choices. We can then multiply the product 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 to get the total number of 40,320 arrangements of non-attacking rooks on an 8x8 chessboard. Let's finish with a final related question. How many ways can we place 4 rooks on a 4x7 chessboard in such a way that no rook can attack another? Here's one such arrangement, and let's take a look at a couple of other ones to see how this is different. Can you use the principles now to figure this out? And does anything change if you assume that the rooks are all distinct or different colors as they were pictured?